Related rates is one of those topics that you'll need to know. There's always a related rates problem on the AP Calculus test. If you kind of know what to watch for and the way that the wording is in the problems, then you'll know that those are the related rates problems. And if you know the process of doing those, then they're actually not too bad. They're a little tricky at first to get a hang of. So let's go through quite a few examples and see if we can go through and figure out what we need to do with each problem. So starting out, let's take this example. A circular pool of water is expanding at a rate of 16 pi inches squared per second. At what rate is the radius expanding when the radius is 4 inches? Okay, so first of all, what you're doing with the related rates problems is they're asking you, there's an equation relating two or more variables. And when these variables change with respect to time, you need to use those derivatives to determine how the rates changes are related to each other. So these rates, they're instantaneous rates, first of all. And so when it asks you what rate the radius is when it's at 4 inches exactly, it's because the pool, if you ever dropped a puddle of water, drop a drop of water on paper, and it slowly is expanding and kind of speeds up and slows down as it goes out. And so at first it spreads fast and then it kind of slows down. And so what that's saying is you're looking for right now what's the instantaneous rate? How fast is it actually moving when that radius is at 4, even though it's not, it's going to continue on, because we're looking at it with relationship to time. Okay, so what we're going to do is let's take, we need to look at the information that they give us and find an equation that relates those to the information that they give us. So on here, so this is the circular pool of water is expanding at the rate of 16 pi inches squared per second. Okay, so that's one of the pieces of information that they give us. And then they also have that then we want to know when the radius is at 4 inches, okay? And we're looking for the rate of the radius. Okay, so this is what we're trying to find. Okay, so what is this? So this is the circular pool of water is expanding at this rate. So this is the area of that circular pool. Okay, so first thing that we want to do is say, okay, so this is area. Okay, this is a radius, and this is the rate of the radius with respect to time. So this is dr dt. Okay, and actually this, and I'm glad I just caught this before we moved on further, this is the rate that the area is changing. Okay, so this is actually dA dt because it's the rate with respect to time. But we need to find something that relates area and radius. So this is where people get hung up, is they say, well, it doesn't give me enough information. They don't know what equation to use. Well, you do have to come up with your own equation. So once you have something that relates area and radius, well, the equation of area is equal to the area of a circle is pi r squared. So right there we have in your just information that you know that area of a circle is equal to pi r squared. So this is the equation that we're going to use. Now, you cannot plug any information into this equation until after you've taken the derivative with respect to time. So I'm going to take this and I'm going to take the derivative with respect to time. So the derivative of area is dA dt. So we're going to leave it as in that notation because we don't actually know what area is yet. And then we have, if you take this whole thing, remember pi is just a number. So this is the same thing really is 3r squared, so you just bring your 2 down. So we get 2 pi r, and then we still, because this variable is not a t, we have to use implicit differentiation, and we need to multiply it by dr dt. Okay. So notice that we are taking the derivative with respect to time, although there is no time in the equation. Okay, so we're taking each of these. All we had to relate was the 2 variables that they talk about in the equation, and you're always relating with respect to time in these types of problems in this test. Okay, so now we have this, and we know now that we have dA dt is equal to, so this is the part where we can start plugging things in. Don't ever plug things in until you've taken the derivative. So dA dt is 16 pi. And we still have this 2 pi here, and then we want to know when the radius is at 4. So we have this picture that's moving and changing, but we want to know the instantaneous rate when the radius is equal to 4. Okay, and we're looking for dr dt. So now that we have this equation, we found the derivative, we can plug in the information we know, we can solve for dr dt. So we get 16 pi equals 8 pi, and I just did that by multiplying the 2 pi and the 4. And then we want to get dr dt by itself, so we're going to divide both sides by the 8 pi. So then we just get 2 equals dr dt. Okay, then you have to relate it back to the problem, because it's really important in the test that you do units and you say what this is. So when you find dr dt is asking what rate is this changing at? Well, notice that this is in inches squared per second. So the rate that the radius is changing. Now a radius is a single measurement. The area is a double measurement, a two-dimensional. The radius is just a one-dimensional, and so this will just be 2 inches per second. Okay, so that's how fast that radius is changing. Okay, so it represents the rate that the radius is changing when the radius is at 4 inches. Now, also just something to note is that the 2 inches per second tells us that the radius is increasing. It's getting larger. If it was -2, then that would tell us that it was decreasing. Okay, so let's look at another example. Okay, so you have a 25-foot ladder and it's leaning against a wall and it's sliding to the floor. The foot of the ladder is sliding away from the wall at a rate of 15 feet per second. How fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? Okay, so you have once again the same thing, and these problems always will give you a rate. They'll always give you I shouldn't say always, sometimes there's differences, but it gives you the information that you need, but you have to come up with your own equation. Now, a lot of times the best technique to use is to draw a picture. A picture is going to help you out a lot. So you have this wall, and you have a 25-foot ladder. Okay, and you have, so it creates a right triangle because this wall is straight up and down. Now the ladder is not going to change. It is always going to be 25 feet long. So in this situation, that is something that you can label before you take the derivative because it's something that does not change. Okay, the ladder is not getting shorter or longer. It's just sliding down this wall. So this is something that's changing, is this is moving down the wall right here. And this side of the ladder is moving away from the wall right here. And those are measurements that they're looking for. Now they also, if you labeled this as 7 feet from the ground before you take the derivative, you have stopped the picture from moving and you're not going to get the right answer. So remember, you first, before you label anything that is changing within the story, you do not do that until you take the derivative. So first thing we need to do is find some way to relate these measurements. So we're going to go through, so let's call this y and this x because that's kind of what it looks like on the range. And we're going to go through and find an equation that relates those two together. So this one, because we're dealing with a right triangle, we want to think through and think, okay, well, what formulas do we know that involve a right triangle? We don't know any of the angle measurements except for your right angle, and those angle measurements are changing also, which is fine because these are changing. But something that we can do with right triangle is use Pythagorean theorem. So we know that we have x squared plus y squared is going to equal the 25 squared. Okay, not 25 once again because the ladder's not going to change. Okay, so now we have an equation that relates the variables to each other. We're going to take the derivative of the equation with respect to time. So we're going to look at what is happening to it as time goes on. So on here now, we're going to take, remember the variable is x, and so when you take with respect to t, you just have to use implicit differentiation. So we're going to have 2x dx dt plus 2y dy dt. And that is going to equal 0 because 25 squared is just a number, and when you take the derivative of that number, it gives you 0. So you didn't really need to multiply that out if you don't want to. Okay, so now we just plug in the things that we know and we're able to solve. So once you take the derivative, you're going to plug in the variables that you know. So I'm going to take, we know that the rate that it's sliding away from the wall is 15 feet per second. Well, on here, that rate is x. Okay, so we know that x, or dx dt, I should say, is 15 feet per second. So this rate here is 15. Okay, and then we still have our 2x. So we're going to have to find some of this stuff here real quick, sorry. So, and we want to know when the top of the ladder is 7 feet from the ground. So this here is going to be what our y value is. This was the dx dt. So we need to find what the x value is. So there's one piece of missing information. But if we know that now we're looking for, in the second step, when this is equal to 7, and we know that this is 25, then we can find x using the Pythagorean theorem also. So I'm going to take 7 squared plus x squared equals 25 squared. You do all the math and you come up with the fact that x equals 24, okay, because we plugged in that 7, and I'm not going to go through that process right now just to shorten the video. So you need to go through and solve for x on that. Okay, so when y equals 7, x equals 24. So we're going to have 24 put in here. And then we're going to also have plus 2. We know that y is equal to 7, and we are looking for dy dt. Okay, so now we just need to go through. We have everything filled in except for the variable we're looking for. Oh, so I forgot to mention, when it asks you what you're looking for, so it says, how fast is the top of the ladder sliding down? It really helps if you write down, okay, that I am looking for dy dt. For me, that helps. This is what you're looking for, is the dy dt. Okay, so then we're going to go through and we're going to, once you plug in everything here, you have 2 times 24 times 15 plus 2 times 7. So this part right here, sorry, let me just do it real quick on my calculator. We're going to have 2 times 24 times 15, which gives us 720. Plus, this here is 14 times dy dt equals 0. So now I'm going to subtract the 720. So I have 14 dy dt equals a negative 720. And then we have dy dt equals negative 720 over 14, okay, which is the same thing as negative 360 over 7, just reducing it there. Okay, so now when you have this, remember we need to look back now and find what our units are. What is it actually asking us? Well, dy dt is how fast the top of the ladder is sliding away from the wall. So it's this rate here of how fast it's moving. Now this ladder is sliding down at a rate of feet per second. And so when this is moving, it's also moving in a single dimension direction. So this will also be feet per second. Okay, so you have negative 360 feet per second. Now, why is it negative? Remember on the other problem, it gives us the direction that it's moving. So notice, because this is moving down, y has a negative rate. It is decreasing at this rate, not increasing, because that y value is getting smaller as it's sliding down. So let's go through this example and try and point out some of the steps that we're going to take when solving these problems. It is the same steps basically, but you do have to come up with your own equation. So, let's go through. The first thing, so let's read the equation. A spherical balloon is expanding at a rate of 60 pi inches cubed per second. Now it's inches cubed because if you think of it as this balloon that's blowing up, it's a three-dimensional thing. It's happening in 3 dimensions. It's a volume. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? Okay, so what's the first step that we need to find? Okay, so the first thing you need to do is identify given info and find what you need to and what you need to find. Okay, so the given information is that you have this rate of 60 pi inches cubed per second. So we know that, and this is a volume measurement, so we know that the rate that the volume is changing with respect to time is equal to 60 pi inches cubed per second. Okay, so this is what we know. We also know that we want to find when r equals 4 inches. Okay, that's what else we want to find. And so we need to find, on here it says, how fast is the surface area of the balloon expanding? So now what we need is we need to find the surface area and the rate that it's changing with respect to time. Okay, so now we need to find an equation that relates those together. So step 2. So once you've found the equation that relates the two variables, that's when we can start taking the derivative to plug in the information. Now, this is a little bit trickier of a problem. You do need to know there's a volume and a surface area function. So we're going to use the two of them together. Now, most of the time you will just use one, but we're going to do this little trickier problem together also so that you're prepared for something like this as well. Okay, so the volume of a sphere is equal to 4/3 pi r cubed. Okay, the surface area of a sphere is equal to, and I'm going to call it S for surface area. You can also call it A if you'd like. You get to choose when you're doing this, but this I'm going to call surface area of a sphere is 4 pi r squared. Now, you can decide, if I were you, I'd put these on flashcards so that you have them. You will be expected to know certain equations. I can't tell you what ones will be on because I don't know, so it's good to be prepared for those. Okay, so find the equation that relates these two rates. So the first thing is we have on here, we do know Vt, dV dt, and we can find, using this information, we can find dr dt. And if you notice that that is the other, that's going to be the other variable that's in this. So we can use this derivative to find the dr dt, and then use that derivative to find ds dt. So we're going to first take the derivative of the volume. So dv dt with respect to time always. And then we're going to remember the pi is just part of the number. Bring the 3 down. So 4/3 times 3 is just 4. Pi r squared, and remember implicit differentiation, this is an r with respect to t, so we get dr dt. Okay, so let's plug in the things that we know. So dv dt is equal to 60 pi, and then we have 4 pi when the radius is equal to 4 squared, and that's going to give us our dr dt. Okay, so then we have, when you calculate all of this and simplify it down, you can find, I'm trying to skip some of the little algebra steps just to make this video not quite as long, so I'm sorry if that, I hope that doesn't frustrate anyone here. So then we have, so dr dt is going to be then 15 16ths inches per second. So this, when you simplify everything out, is 15 16ths inches per second. Okay, and that is the rate that the radius is changing when the radius is at 4 inches. Now, so think of this, you have this balloon that's blowing up, and that's how fast the radius is changing at that moment. Now, we are not asked in the problem to find the radius. It's not asking to find the rate of the radius. It's asking to find the rate that the surface area is changing. So now let's take the derivative of this one with respect to time. So ds dt equals, bring down the 2, we get 8 pi r dr dt. And now we have the information that we need from this to solve for ds dt, which is what we're trying to find. So this step is really important to find, to know what you're looking for. Okay, so ds dt equals 8 pi when r equals the 4 inches. And when at that moment, we know that dr dt is 15/16. Okay, so then we have ds dt equals, when you plug in all of that information, we get 30 pi inches squared per second. Now remember, so why is it inches squared per second? You get inches squared because now that you're dealing with a surface area, it's a two-dimensional measurement. Okay, so we have here 30 pi, and you can leave it in terms of pi. You really don't need to multiply the pi out. But let's really quickly add this last step in that the third step is to look at what the problem asks for and use units in your answer. It's really important that you have those units because you get a point just for having those. So the answer you're looking for, ds dt, is 30 pi. And remember that now you know that this is in inches and this is a two-dimensional measurement. So you have inches squared per second. Okay, this next example I want to go through is even more tricky, but it is one that it is also a typical problem that you may see. And so I want to go through it. You will have one on your homework. A lot of the ones are more basic, like the others on your assignment you'll see. But this is another one that's tricky, so I'm going to give you the keys to answer this type of a problem. Okay, so you have a conical tank. So it's a cone, and it's standing on its vertex, and it's being filled with water. Well, the thing that you need to know to get this right is that the ratio of the height of a right circular cone is, and to its radius is constant. So what that means is that at any level that the height of the water is going to be twice its radius because it has this constant thing. So we know that at any point, sorry, let me change my color here, height is equal to that 2r. Okay, so anywhere where the height is, because it's consistently working together, the radius will be twice as large. Okay, so that's just something that this cone has in common. Okay, so see a beautiful picture right now. So as this is filling with water, so there's my little shark water. Okay, so this height and this radius are related to each other, and that's not a radius, that's a diameter, but you got what I mean. So just this half part are related to each other. Okay, which means it's probably a lot deeper. Anyway, okay, so we have the height is equal to that. Okay, so what is it, first of all, what is the information that they give us? So it's being filled with water at a rate of 18 pi feet cubed per minute. So this is equal to the volume with respect to time. If the tank has a height of 30 feet, okay, so this is our standing rate, and the radius of 15 feet. So see how they tell you right here that the height it's a consistent measurement, and so the height is going to be equal to 2 of the radius. How fast is the water level rising when the water is at 12 feet deep? Okay, so we want to know how fast that height is. So we're looking for, in this problem, we're looking for dh dt, right? So this is what you're trying to find, is the height. This 12 feet is the height measurement. Okay, so we need something to relate these together. So we're going to take the volume of a cone. So the volume of a cone is equal to 1/3 pi r squared h. Okay, now we don't know how yet. We're going to learn this more. You'll learn how to derive this formula using integration later on. So I'm going to just first take, and we're going to make some changes so that we can solve this, because you have two variables multiplied together here, and we're taking it implicitly. So what we're going to do is we're going to say, okay, we can substitute in, instead of r, I want to make it so this just has a measurement of h. So we know from here, if we divide both sides by 2, that r equals h over 2. Okay? So if r equals h over 2, we can substitute that in. So we're going to have v equals 1/3 pi h over 2 squared times h. Okay, so then we're going to multiply those together so that we have just something that is easier for us to take the derivative of. Okay, so we have here, when this squares, you get h squared over 4. And so those two multiply together, you get 1/12. And then you're going to have pi h cubed. Okay, so now that we have the variable, so that's the trickiest part of it. And so when you do this, the one that's a cone in the story problems in your homework, refer to this example to help you through it. And hopefully then you'll be able to kind of see it. And this is something you might want to go over before the test again as well. Okay, so we're going to take now and we're going to find the derivative of this. So we're going to take dv dt with respect to time, multiply by 3, you get 3/12, which is the same thing as 1/4. Pi h squared. Remember, it's implicit differentiation. You need to do dh dt. Okay, so now that you have this, we are trying to find, remember, we're trying to find the dh dt. We know that this is dv dt, so we're going to plug in 18 pi. I'm going to just reduce that down to the 1/4. And then we have 1/4 pi. The h, the height that we're looking for, is when the water height is 12. And that's going to give us our dh times the dh dt. Okay, so when you go through, you're going to simplify that, simplify that down and solve for dh dt. Now, dh dt in this problem then is going to be 1/2 a foot per minute. Sorry, so make sure you have the measurements too. So this gives you, when you reduce everything down, 1/2. Now remember your units. This is asking you how fast the rate that the height is changing. A height is a single measurement, and we're working here with feet and minute. So when we go through, we're going to have 1/2 of a foot per second. Oh, I keep saying second because that's always the first thing that comes to mind is minute. Okay. So, so hopefully you'll be able to do that too. Come to class with any questions that you have, and I'll be able to help you set those up. Try a couple of them at home at least. You'll have better questions and know what to ask if you try these on your own.